This is Manu from eBay. I'm super excited today to speak here at the inaugural Iceberg Summit. In this session, I will share about our journey with Iceberg at eBay and the valuable lessons we've learned along the way. Hope you will enjoy the next 30 minutes. So let's get started. First, a bit about myself. I'm part of eBay's Hadoop team and work on the cloud data platform. My focus is on developing customized Spark and Iceberg, building data architectures to serve various data applications at eBay. I'm also passionate about contributing to open source projects, and I'm the maintainer of 42 awesome projects that you may find interesting. Okay, this is today's agenda. We will start with the evolution of eBay's data architecture, and then we will move on to the current data architecture we are building around Iceberg. Then we will explore two common use cases at eBay in depth. To conclude, we will touch on our future plans of improvements to our platform with Iceberg. Okay, now let's take a time travel and look at the evolution of data architecture at eBay. So you might be very familiar with this diagram if you read Databricks blog on the concept of lakehouse. I've adapted to better reflect eBay's history and current status. So eBay's data architecture started with vendor warehouse around 20 years ago. During that time, we loaded structured data using ETL processes into the data warehouse and mainly served data analysis purpose. Then we entered into the big data era. The volume, velocity, and the variety of data grew dramatically, as did the cost of the vendor warehouse. Meanwhile, in addition to the data analysis applications, our users have a wider range of data applications such as real-time monitoring, data science, and machine learning. That has prompted us to transition to a Hadoop warehouse, which are built on open source Hadoop projects such as HDFS, Yarn, HiveMaster, and Apache Spark. Although this architecture has served us pretty well, it lacks essential features like transaction support, fast updates, and data quality, and data governance. And what if we can? Our users usually need to work around these limitations with a complex pipeline on their own. So what if we can hide the complexity and provide our users with a SQL-like experience with all those fancy traditional database features? This is precisely what Iceberg offers as an advanced table format. And that's why I prefer to use a SQL warehouse instead of the lakehouse, because it accurately describes the user experience we are of the data architecture we are building with Iceberg. And now let's examine it in details. So in our data architecture, Iceberg is at the center and has proven to greatly improve the efficiency in various use cases. Thanks to its faster capabilities of fast updates with ACID guarantee, our users no longer need to overwrite the entire Spark table just to update a small amount of data. Meanwhile, this can be expressed efficiently in a very simple merging to query. And schema evolution, including partition evolution, is another great feature that saves our users from repeatedly rebuilding their tables for any schema or partition changes. In addition, time travel and rollback through single queries add even more value for our users. We developed our customized catalog that checks namespace and tables in the Hive Meta store. That ensures very smooth compatibility with existing Spark and Hive tables. However, we commit with Hadoop operations to avoid any potential performance issues with the Meta store. It's kind of combining the best of the Hive catalog and the Hadoop catalog. So I call it the Hive Hadoop catalog. In our data platform, the data usually ingested from Kafka, loaded and transformed with Spark or Flink and into the Iceberg tables. The underlying Arrow, metadata in Arrow and data in Parquet are both stored on HDFS. And most of the data applications are written in Spark. And all the table commit events are sent to a lake manager, which will schedule maintenance jobs with Apache Airflow and also sync metadata to the meta store. We will talk about the lake manager in detail next. So currently we have over 200 Iceberg tables, all in V2 format and with merge on read write mode enabled. Okay. One caveat of the Iceberg is that the improved efficiency is not free. It comes at the expense of slower reads and increased small files that might overload the HDFS name node. To address this issue, we've developed a dedicated service called Lake Manager that will schedule maintenance jobs to merge small files and eliminate deleted files to enhance the read performance. Triggered by the commits, it will decide the best time to run the maintenance jobs. It will avoid scheduling unnecessary jobs while utilizing the idle resources on the cluster. In addition, it will also purge expired and orphan files to optimize storage efficiency. Last but not least, it will also sync table metadata like last commit time, last completion time, the total number of data files, the total number of delete files to the meta store for analysis. Another responsibility of the lake manager is to merge the changelog events in the near real-time pipeline, which we'll discuss later. Okay, now let's dive into the two common use cases with Iceberg at eBay. The first case is from the data compliance requirements like GDPR. So our users are required to delete expired data periodically within a very tight timeline. Another challenge is that they don't want to alter their business logic because there are so many such pipelines. And their automatic process also require idempotent run on any failure. And any changes are not expected to have any impact on the downstream users. So our Iceberg solution is to append an add files procedure to the business logic. The adherence procedure will import a Spark table partition into the Iceberg manifests without copying any data. And then we can run the first Iceberg delete commands, which will mark the delete position, deleted rows in a delete files. It's very fast. And meanwhile, we utilize Iceberg's Tag DDL to check snapshots for rollback. Okay, here is the detailed workflow of processing partitions from a Spark table partitioned by date. In the first step, we set the current snapshot to the tag of after after processing a previous partition t-1, and then the partition of current partition the current partition t is imported into the Iceberg table with the advice procedure. Next, we run the delete from query to remove data older than 12 months in partition T. After this is finished, we can mark the current status by creating the tag T. And then we can update the view for downstream users by switching from partition t-1 to partition T. If any of these steps fail, we can always return to the first step, and by resetting the snapshot to the tag t-1, which is the status of the previous partition, and it will return the exact same results on rerun for any times. Although this process has been very smooth and efficient for our users, it's not as quiet as it looks beneath the surface. Firstly, the adherence procedure will read files sequentially to check them in the manifest, which is very slow if you've got like thousands or tens of thousands files. We parallelize the file reads and contribute back the enhancement to the community. Another issue that after writing the data files, there is an updated copy of the original Spark table partition, and resulting in double storage. Hence, we also need to take care of purging the Spark table partitions. We also need to remember updating the tags in the maintenance jobs like read the files procedure. Otherwise, these commits will be lost when we resetting the snapshot in the first step of our process. We will also encounter issues when reading Parquet 96 columns for timestamp values. And note that all table partitions imported into Iceberg will be checked by the latest snapshot, so they will never expire. So we need to develop an extra procedure to delete those old partitions at the folder level. Iceberg doesn't support a folder level delete natively. Given all these issues, if time permits, I still recommend our users to rebuild their pipelines and rebuild their data tables in Iceberg. Now move on to another common use case with Iceberg at eBay, the near real-time pipeline. In the near real-time pipeline, change data capture events are pulled from a database through Kafka and loaded into our data platform with a Flink. And the change events are then applied, and then our downstream users can analyze the data within minutes to hours delay. The most straightforward approach here is to use the Flink upload mode with Iceberg, but the performance, the read performance of with upload mode will decline when the number of the equality files accumulate over time, and our maintenance jobs cannot catch up. So we devise a two-table approach with our users. In this approach, the change events are firstly appended into a changelog table. Then another Spark job is scheduled hourly to merge incremental changes to a fact table for analysis. The incremental changes are generated by the create changelog view procedure. This process has been running stably for the users, but it does require complex management. Therefore, we are developing a solution that can hide the complexity from users, and they only need to interact with the fact table. In this process, when a fact table is created with a CDC configuration, a changelog table is generated automatically behind the scene. And when the data are loaded into the fact table, it's actually first appended to the changelog table first. Then our lake manager will monitor the changelog commits and schedule Spark merge job periodically. And our users can tune the data latency by configuring the schedule interval of the merge job. In addition, any schema changes applied to the fact table are also applied to the changelog table behind the scene. This work is still in progress, and we will share more when it's rolled out. Our journey with Apache Iceberg has actually just get started, with many exciting possibilities ahead. For instance, implementing a data copy for disaster recovery can greatly reduce the required bandwidth between clusters. And to further enhance the read performance, primary index and second index is worth checking out. And we also plan to experiment with rewrite in sort order or the order, which can also improve the computing efficiency. In addition, write with higher compression level can help to save a lot of storage. Data security is another important subject that we are exploring integration with Apache Ranger. Last but not least, our metadata are currently stored manually synced to the Hive meta store for analysis. It's incomplete and inconvenient for analysis with very high latency. So we are also checking out the open source write catalog services like Gravitino. Okay, here are some references that you might want to check out. To sum up, our journey with Apache Iceberg has been wonderful so far, and we can't wait to see what's in store for us in the near future. That's all for my session. Thank you. And any questions?
Yeah, thanks, Manu. That's really great. We have some questions on the chat, so let's use from the bottom. So the first question is the Hive Hadoop catalog is a custom catalog implementation you did, or is the one provided by Iceberg?
It's a customized catalog. We did a very similar to the Spark session catalog provided by Iceberg. With this catalog, we can read both Iceberg tables along with the Spark and Hive tables. Yeah.
Gotcha. Second question is, how do you remove the delete files? Do you remove the orphan files, or you actually rewriting the manifest and rewriting the data files?
When we remove delete files, we do rewrite the write the whole data files along with the delete files to generate new data files, and we also run another procedure that will remove the expired files and the orphan files as well. Yeah.
Okay. And I have my personal question about that. Are you using a query delete or positional delete?
We use position delete for Spark merging to and equality delete for Flink afterwards. Yeah.
Okay. Makes sense.
Yeah.
Another question is, cool Iceberg cherry pick feature to be used for the ingest pipeline instead of using an intermediate table?
I suppose it's ingest pipeline means the CDC near real-time pipeline, right?
Yeah.
I haven't thought about the cherry pick feature yet. I'm not sure what's how can I utilize it for this
I don't know.
pipeline.
Yeah, to be honest, I don't know either. Another question is, can you use merge on read to append records coming through Kafka directly, avoiding building a lot of changelog?
With merge on read, I think you mean the Flink observe mode, right?
Yeah, I think so.
Yeah. So as I mentioned, with the observe mode, the equality delete files will accumulate, and by our experience, our maintenance jobs cannot catch up to remove those equality delete files, and the read performance will decline over time, and it will become a severe and more severe. Yeah.
Okay. Another question is, what is the table size and daily ingest size you face? What's the amount of data you have every day, almost?
And we are talking about the TB level data size, but the change will usually around the GB level, like maybe 1% of change to those TB level table. Yeah.
Okay, we have a few questions about the lake manager that you mentioned. So basically, there are two questions, in my opinion, that are related. First is, how do you orchestrate your pipelines using lake manager? Is lake manager responsible of orchestrating the pipelines?
No, our users will orchestrate their own pipelines with the ETL process. Yeah.
Okay, I see.
So the lake manager is actually working behind the scene to schedule the background jobs, so it's invisible to the users. Yeah.
Okay. Related to that, and also ingestion, is how do you have any issue with your maintenance job conflicting with the regular data ingestion jobs? Like you have you said that your lake manager do all the, I guess, the compaction and all this stuff. Does it conflicting with the ingestion jobs you have?
Yeah. Sometimes it will conflict, and sometimes it fail, but we enable the partial progress, at least to at least make some progress. And on failure, I think the compare job has the retry on failed commit. So eventually it can, I think eventually in our cases, eventually it can succeed in rewriting the files. Yeah. Mm-hmm.
And to deal with that, for instance, the Tabular Kafka Connect injector for Iceberg is using the commit coordinator to to synchronize the commits on table. Do you use something like that, or do you create something on your own, like ordinance of the commits in the Lake Manager, something like that?
We don't have something. Do you mean my scheduled commits to like to work to like resolve the conflicts, commit conflicts in the link manager? Oh,
yeah.
Sorry. Could you?
Yeah. So basically, if
repeat?
you have multiple writers at the same time on the same table, you may have some kind of conflict. So do you just do a retry mechanism, or
yeah. We just do the retry. Yeah.
Okay, gotcha. Because there are two approaches for that: the retry, or we have a kind of single, idempotent component that manage all the commits in the order, and so we are sure that we committing in the right order and we don't have any conflict. So basically, in the Tabular Kafka connector, they are using another topic to deal with the commits.
Okay. So it's actually another benefit of using a REST catalog where you can resolve those commit conflicts at the server side. Yeah.
Okay, makes sense. And about the retry mechanism, in case of a failed commit, do you do a number of retry, or do you have some kind of exponential backoff or something like that?
Yeah. So with I think Iceberg has a native support for configuring the retry times on failure, and we also schedule. Since we schedule those maintenance jobs with Airflow also has a retry configuration, so we can also retry for multiple times. And our users also have a retry mechanism in their ETL pipeline. Yeah.
Okay, cool. I don't see other question from the Q&A tab. So yeah, thank you again, Manu. Very nice session. Really appreciate it. I hope you guys also appreciate it.